Have you ever just stopped and wondered how an AI goes from being kind of clueless to all of a sudden brilliant? I mean, it's one of the biggest, most fascinating puzzles in tech right now. We're not talking about a slow, steady climb. We're talking about a sudden, almost magical leap in intelligence. Okay, let's dive into this mystery.
So to really get this, we have to start with this really strange thing that AI researchers noticed. They've figured that as they built bigger and bigger models, the improvements would be pretty straightforward. A little more data, a little more power, a little smarter. But what they actually found was something else. Something that just didn't follow the rules.
Okay, so check this out. It's like a tale of two different models. You give a smaller AI a pretty simple 3-digit math problem, and it completely bombs. I mean, wrong almost every single time. Now, you take a much, much larger model, you give it the same kind of problem, and it doesn't just get a little better, it suddenly becomes an A student, nailing the answers with crazy accuracy. And here's the kicker. The skill just wasn't there at all, and then, bam, all at once, it was.
So this leads us to the big one, the question at the heart of all of this. How on earth does an AI suddenly learn to think? It's not slow and steady, it's like a light switch gets flipped. And for the longest time, this was a total black box, a mystery that scientists are really only just now starting to crack.
Well, it turns out scientists now have a name for this crazy phenomenon, emergence. And this whole explainer is going to be a deep dive into the groundbreaking paper that really dragged this mystery into the light. A paper called Emergent Abilities of Large Language Models, which finally started to connect the dots.
What's cool is that this idea of emergence isn't even brand new to AI. It actually has its roots in this really profound concept from a Nobel Prize-winning physicist, Philip Anderson. He famously said, "More is different." What he meant was, when you add enough quantity to a system, more water molecules, more brain cells, or in our case, more parameters, and an AI, you don't just get more of the same stuff. You can get something totally new, a complete change in what the system can do.
And that brings us to the official definition from the paper. An emergent ability is basically a skill that is, for all intents and purposes, absent in smaller models, but then it just pops into existence in the larger ones. And this means you can't just look at how the small models are doing and draw a straight line on a graph to guess when the next skill will show up. The old rules just go right out the window. Honestly, the best way to get your head around this is with a super simple analogy. Water. Think about it. A single H2O molecule. Is it wet? No. A handful of them? Still not wet. But when you get trillions and trillions of them all together, they suddenly have a brand new collective property, wetness. Wetness emerges from the sheer quantity. It's a property of the whole group, not the individual parts. And that is a brilliant picture of what's happening inside these AI models. Okay, so the analogy is great, but you're probably thinking, all right, where's the proof? Show me the data. How do we know this is actually happening? Well, researchers have been able to fingerprint this phenomenon by tracking model performance super closely as they scale up. So let's follow the evidence and see what these fingerprints look like.
And what they found is this really clear pattern, something you can call the hockey stick jump. For a long, long time, as a model gets bigger, its performance on some specific, tough task just stays flat, like down at near random guessing. It's learning, sure, but not in a way that helps with this one skill. And then it hits some critical size and the performance curve just whoosh shoots straight up.
And here it is in action. This is that 3-digit math problem again. Look at the small models. They're just guessing. Accuracy is basically zero. But once they cross that size threshold, around 60 billion parameters in this case, the ability to do math just appears. It's not a gradual curve up, it's a switch being flipped.
And just to prove this wasn't some one-off fluke, we see the exact same hockey stick pattern with other things, like unscrambling words. Again, the smaller models are hopeless. Then, at a certain scale, they suddenly crack the code. Seeing this happen over and over told researchers they were onto something huge.
But wait, because this is where the story gets even stranger. It's not just what the models can do that emerges with scale, it's also how we can talk to them and get them to work. Turns out some of our best tricks for making an AI reason are totally useless on the smaller models. Take this puzzle, for example. There's this technique called chain of thought prompting. It's basically where you ask the AI to think out loud, to lay out its reasoning step by step. Now, on a small model, this trick doesn't help at all. In fact, it can actually make it do worse, like you're just confusing it. But on a large model, it's like unlocking a superpower. It becomes a genius. The ability to even use this kind of guided thinking is itself an emergent skill. So we've seen the what. We know these sudden jumps in skill are happening. Now for the much, much harder question, why? Why does just making a model bigger cause these new abilities to just switch on? What is actually going on under the hood? But before we go any further, we have to ask a really important question, one the researchers themselves had to deal with. Is this a real, genuine jump in the AI's core ability, or is it possible it's just an illusion created by the way we're scoring it? So the paper offers up a few clues. First, maybe some complex tasks just need a certain number of steps to solve, a kind of mental workspace that only really big models have. Second, maybe the bigger models are just way better at memorizing all the random world knowledge you need to connect the dots. But the most interesting idea is that maybe our pass-fail scoring system is the problem, that it's hiding all the tiny improvements happening underneath.
So researchers looked deeper, using different ways to measure that could see that gradual improvement. And yeah, it turns out the smaller models are getting slightly better in the background. But that doesn't explain away the mystery, not even close. So while how we measure things is part of the story, it's not the whole story. The sudden, dramatic jump in useful skill, it's still very, very real. Emergence isn't an illusion.
Now, up to this point, we've been talking about all these amazing new skills like math and logic. But the whole unpredictable nature of emergence, well, it's a double-edged sword. Because if these powerful, good skills can just appear out of nowhere, it forces us to think about a much more serious possibility. And the question we absolutely have to ask is this: if good abilities can emerge without anyone programming them in, without anyone even seeing them coming, what else can? What other behaviors are just sitting there dormant in these massive systems, just waiting for the right amount of scale to wake up? And this, right here, is the dark side of emergence. Researchers have found that as these models get bigger, they can also unpredictably pick up some really negative traits. They can get better at mimicking fake news or start memorizing and spitting out private data they were trained on. The risk that entirely new, harmful behaviors, like deception, could just emerge becomes a very real and serious concern.
And that brings us to the final and maybe the most important piece of this puzzle. Understanding emergence isn't just a cool science experiment. It fundamentally changes how we have to think about the future of AI.
Take a look at this list. This is the frontier. These are all tasks where even our biggest, most powerful models today are still at zero. They completely fail at things like formal logic, or even playing a game of chess just by reading a list of moves. Every single one of these failures is a candidate for the next unpredictable emergent breakthrough. We have absolutely no way of knowing which domino is going to fall next, or just how big the model has to get.
And that leaves us with this one last thought. The biggest breakthroughs in AI, the ones that change everything, might not come from some clever new algorithm someone designs. They might not be planned at all. They might simply emerge the next time we cross some invisible threshold of scale. And the only question that really matters is, will we be ready for them when they do?